Alright, hi everyone. I'm finally going to try to continue with this series and hopefully finish up what I started. Let's start by recalling where we were and what we were trying to prove. So today's lecture, we're really only going to focus on one thing, that's the efg theorem. Okay, so let's start by recalling what this theorem even says. So this will be Theorem 33.1.1. So the efg theorem is all about understanding how ideals in a base field factor in an extension. So we're going to start with some degree m extension of number fields. And we're going to also start with a prime ideal P in the ring of integers of K. And we're going to suppose that the primes lying over P are these big P sub i's. So these big P1 through big PG are the primes dividing P O sub L. Okay, so what this theorem tells us essentially is it tells us about the ramification, the residue degree, and the number of primes, and it relates all these numbers. So the theorem says, in the most general setting, that the sum of the ramification degrees times the residue degrees equals the degree of our number field. And here the E sub I is the ramification degree of big P sub I over little p, and F sub I is the residue degree. Okay. If we have the additional information that L over K is Galois, then we can say that all the E sub i's are equal, and all the F sub i's are equal, so that our equation above here just becomes E times F times G is equal to M. So this is kind of where the theorem gets its name. Here, the E is the common value of all the E sub i's, and F is the common value of all the F sub i's. Okay, so why don't we go ahead and jump right into the proof of this fact. So the previous lecture was pretty much set up for this proof. So we're going to kind of rely on some of the lemmas we used, or we proved in the previous case. And there are really two claims here. So there's the general claim, and then there's the Galois case. And the proof will kind of naturally break up into two different pieces. So we've got claim A. Claim A says that the sum of these residue index times the ramification degree times the residue degree is equal to the degree of the field extension, and then there's the claim B, what happens when our field extension is Galois. Really what we need to show is if L over K is Galois, then E sub I equals E sub J, and F sub I equals F sub J for all I and J. Okay, so let's go ahead and just worry ourselves with claim A to begin with. Okay. So the basic idea is that we're going to exploit the lemma from the previous example, which allowed us to compute the index of B sub I to the E sub I and O sub L. And then we're going to use the Chinese remainder theorem or Sun Tzu's theorem to break up our quotient into a product and get our equation from claim A. So since all these big P sub i's are coprime, because they're distinct primes in our Dedekind domain, we have, by Sun Tzu's theorem, we have the following factorization of O sub L mod P O sub L. So I know the factorization of P over O sub L is the product of these P sub i's to the E sub I. So this is going to factor as this product from 1 to G of O sub L mod P sub I to the E sub I. Okay. So once we have this factorization, then we know that if we compute the dimension as O sub K mod P vector spaces on both sides, that should be the same. So let's just think for a minute about how we're interpreting both of these things as O sub K mod P vector spaces. So this thing is O sub L contains O sub K as a subring, so it's naturally an O sub K module, and P acts trivially on this space because we're modding out by P. So it inherits the structure of an O sub K mod P module, and because O sub K is a Dedekind domain, and P is a prime ideal, it's also going to be a maximal ideal. And so O sub K mod P is a field, so I'm thinking of this thing as a vector space. And then similarly, P is contained in each of these ideals, and so P will also act trivially on all of these product factors, and you can think of each of these as O sub K mod P vector spaces as well. If we compute the dimension on both sides, well, we know how vector space dimension acts over products, so we essentially get O sub L mod P O sub L. So the dimension of this space is, well, it'll be the sum of the dimensions on the right-hand side. P sub I e to the I over O sub K mod P. And here we can use the lemma we proved in the last lecture. Each of these is equal to the product of the the ramification degree times the residue degree. And so this equality here is due to the last lecture. Okay. So really we just need to show that the dimension of this thing is equal to the degree of the extension. Sorry, not E, but M. And once we show this, this will prove claim A. And the basic idea is that if you take a basis for O sub L over O sub K as an O sub K module, this basis will basically just immediately descend to a basis on O sub L mod P O sub L. However, we have to remember that if O sub K isn't a principal ideal domain, then this isn't actually, O sub L is not necessarily a free O sub K module. So let's kind of remember exactly what we showed about O sub L as an O sub K module. So recall, so if you go back to lecture 22, we had the following proposition. We have proposition 22.1. And what this says really is that we can sandwich O sub L between two free rank M O sub K submodules. So we can find two rank M free O sub K submodules of L. I'm going to call them M, and these are going to sandwich O sub L and M sub prime. And so yeah, I guess let's just pause here for a minute and think about what's going to happen next. Essentially, the idea is when I tensor with O sub K mod P, this is going to be a dimension M vector space. This is also going to be a dimension M vector space. And so we're going to sandwich O sub L mod P between two dimension M sub vector spaces, so it too will have to be dimension M. Let me just say a bit more about that precisely. So we have isomorphisms of O sub K modules, right? Because these things are free, we can really say that M is isomorphic to O sub K to the little m, and M prime is isomorphic to O sub K to the little m. And you can quickly check that, well, if you look at the map from if you look at the map from O sub K to the M to O sub K mod P to the M, so this is just a natural projection in each factor. This will be surjective with kernel P to the M. Okay, so I would say this statement, P O sub K to the M. I would say this statement is almost trivial. Okay. So you can see that O sub k mod p O sub k to the m is isomorphic to this space using the first isomorphism theorem. And what we ultimately get, we get a sequence. So this sequence of inclusions, you can think of these inclusions really as injective maps. And this sequence of injective maps is going to lead to the following sequence of injective maps. M mod PM injecting into B mod PB, and this B should really be O sub L, sorry. And again, this is injecting into M prime mod P to the M prime. And so you might wonder, why do we know that these things are still going to be injective? You can essentially just check this by computation. So I guess really there is like some tiny thing to check here, but I'm not going to worry about it. It is a one-line argument. And we know these outer two vector spaces, sorry, I should say outer two O sub k mod p modules are dimension m. And we know that for vector spaces, it's not possible to sandwich anything other than a dimension m vector space between these two things. So really, these are actually going to be isomorphisms. Thus, we must also have O sub L mod P O sub L. This dimension is equal to m. Okay, so this proves claim A. So the idea was to compute this thing in two different ways. Using our previous lemma, we found that it was the sum of these products, and computing it directly using the fact that O sub L, we can say something about the rank of O sub L over O sub k. Computing that directly gives that is equal to m. Okay, so next let's go ahead and try to prove claim B. And so now we're going to suppose that L over K is Galois. So the key fact that we're going to use here is essentially that the Galois group acts transitively on the primes over little p. So we know that, in particular, we know the Galois group sends primes over little p to primes over little p, and that for any pair of p sub I and p sub j, we can find an element of the Galois group taking p sub I to p sub j. So the idea is we're going to use that first to show that their ramification degrees are equal, and then from there we'll be able to quickly see that the residue degrees are also equal. So we're going to choose any pair I and j between 1 and g. And we know we can find sigma, so that sigma of p sub I equals sigma of p sub j. Sorry, my p's kind of look like betas. They're supposed to be capital math frac p's. Now the key computation is as follows. We know that E sub j is the number of times P sub j divides P O sub O. And because P is an ideal in K, well, sigma fixes K, and so P sub O sub L is the same thing as sigma of P O sub O. You can basically just think of the fact that sigma takes O sub L to itself, and sigma fixes P. So you could imagine pulling this P out in front, and that will give you this equality here. If we think about trying to compute this, let's think about the different ways that we could get a P sub j in sigma P of O sub L. Well, since P is invertible, since sigma is an invertible map on L, sigma of P sub k is going to equal P sub j if and only if k is equal to I. So if you had another prime ideal that mapped to P sub j, you could essentially apply sigma inverse and find that that ideal had to be P sub I. Hence, the only factors contributing P sub j's to sigma of P O sub L, the only ways to get P sub j's here are those coming from the P sub i's. So really, there's only going to be E sub I factors of P sub j in here. So we started with E sub j and we've gotten E sub I. So we've really proven kind of half of claim B. The remark I want to make here is that this concept, the order of a prime dividing some ideal, this function is really only well defined because we know that in Dedekind domains we have unique factorization. Okay, so let's go ahead and think briefly about showing that the residue degrees are equal now. And the idea is that you want to consider the map sigma from O sub L to O sub L. And we know that sigma fixes, not necessarily pointwise, but that sigma takes P O sub L to itself. With this in mind, you can see that this is going to descend to, so note then that you can essentially get a map from, sorry, I actually don't need this fact. I don't know why I repeated it. What we really need is that because sigma takes p sub I to p sub j, sigma is going to descend to a map here. And in particular, this is going to be an isomorphism. And it's going to be an isomorphism of O sub k mod p vector spaces. So we know that sigma is going to fix O sub k, so it's going to be an O sub k module morphism. MPX trivially on both these spaces, so it's going to be a O sub k mod p vector space isomorphism. And the reason it's an isomorphism is that we can explicitly, I can tell you what the inverse is. It's just take the inverse map to sigma and then take the map that this descends to on O sub L mod p sub j. Once we realize that this is an isomorphism of O sub k mod p vector spaces, the fact that the f sub I and the f sub j are equal just follows from the definition. Remember that the f sub I is the dimension of these things over O sub k mod p. And then finally, the efg fact. The fact that efg equals m just follows from claim A. Okay. So that's the proof of the efg theorem. There's nothing too terribly complicated going on here. The lemmas from the previous lecture really did the bulk of the work. In the next couple lectures, we're going to try to focus on this ramification degree, this ramification index. Trying to say, when does a prime ideal ramify in an extension? Can we say more precisely when that happens? Because it turns out that ramification is I would say it's a bad behavior. It ends up making proofs more complicated. Oftentimes you'll need a special case, or you'll need to completely ignore the case in which your prime that you're kind of looking at is ramified. And it essentially is some obstruction to a local to global practice. So a lot of times you'll be trying to prove something locally, and maybe you can extend your condition locally in the case that your prime doesn't ramify. You can extend your local claim to a global claim for all primes if you know something about the prime ideals, maybe like dividing the conductor of your elliptic curve don't ramify in some field extension. Okay, so we're going to study ramification a bit more in the next few lectures.